Hello.
Hi.
8B quiz tomorrow. Hmm. So we could do the new material for 8B. I think we went over Claisen condensation last night. So we could get started with like decarboxylation, malonic ester synthesis, and acetoacetate synthesis. So let's do um malonic ester synthesis. So malonic ester synthesis is going to be a very specific synthesis route where you're going to start with a ethyl malonic ester, and then there's going to be a few steps. The first step is going to be alpha alkylation, right? The first few steps. Well, to be more specific, let's do actually, yeah, let's just do alpha alkylation 1 or 2 times. 1 or 2 times. After that, you're gonna do hydrolysis, and then the third step is decarboxylation. And what you will get is going to be a carboxylic acid with the 2 or 1 alkyl group that you added. Right? So an ethyl malonic ester is gonna look like this. And let's say we react it with these reagents here. The first step is this base with the solvent. Second step is going to be this alkyl group. Third step is going to be another base with the solvent. Fourth step is going to be, let's say, this molecule here. And then fifth step is going to be acid workup, but I'm going to do H2SO4, water, and heat. And that's going to do a couple of things, multiple things, actually. So what would the first step do to this reactant molecule?
Grab the alpha hydrogen between the
Yes,
two carbonyls.
right. This strong base here, ethoxide ion, is going to look for the most acidic hydrogen, which is the alpha hydrogen between the two carbonyls, because that's going to lead us to an enolate ion where we have a stabilized negative charge, right? That's a stable conjugate base. That means that this is an acidic acidic hydrogen right there, right? So that's the first step. What would be the second reaction when we bring in the second step?
It would react with, oh no, with the Br. It would kick out the Br.
Yes, this is my starred molecule. This is my dot carbon. My starred carbon is going to attack the dot carbon and kick out the Br. SN2 reaction. So when we do that, this is the starred carbon. This is the neo bond between the starred carbon and dot carbon. The dot carbon is attached to 1, 2, 3 carbons, which is this 1, 2, 3 carbon right there. The Br is no longer there. It got kicked out as Br minus. Okay. Now the third step is gonna do the same thing as the first step because we have one more acidic hydrogen here, right? But what we just did with the first two steps there is that we alkylated the alpha carbon. We did alpha alkylation, right? This is the carbonyl carbon right here. This is the alpha carbon between the two carbonyls. And we see that at the alpha carbon, we alkylated it. We added an alkyl group right there. The third step here is gonna bring in the strong base, deprotonate the other alpha hydrogen to create another negative charge, another nucleophile, another enolate ion, right? And when that happens, this is our start carbon again. Now let's bring in our fourth molecule. What's gonna happen between that fourth molecule and the enolate ion that we just formed? What's gonna get attacked? What's our electrophile here?
The it's gonna do 1,4 addition.
Yep, it's gonna do 1,4 addition, also known as conjugate addition, right? This is an alpha beta unsaturated carbonyl, and there's two electrophiles. There's the carbonyl carbon and there's the beta carbon. The irreversible nucleophiles, like the reducing agents and organometallics, attacks that carbonyl carbon, 1,2 addition, direct addition. But the reversible nucleophiles, like this enolate ion, OH minus, OR minus, amine, CN minus, any other nucleophile, right, is gonna do a 1,4 addition, conjugate addition. It's gonna attack this beta carbon right there. So we're gonna attack that beta carbon, shift the double bond over there, pop the double bond onto the oxygen, and now we're gonna connect those two pieces together. And this is the tricky part here. This is why I like starring and dotting my carbons, right? This is my starred carbon here. That starred carbon is attached to 1, 2, 3, 4. And then now this is the new bond between the starred carbon and the dot carbon. This dot carbon here is part of a 5-membered ring like this, and it is not double bonded anymore because we shifted the double bond over here, and it's going to be an O minus right there. Now, what is this that we just formed right here? When you have an O minus next to an alkene, what is the name of that ion? There's a specific name of this ion here.
Enol. Or enolate.
Yes, enolate. An enol would be a neutral alkene with a neutral alcohol.
Okay.
Right? Enolate is a deprotonated enol when you have an O minus. So this is an enolate ion. Okay. Now let's bring in the last step. This last step here is gonna do 1, 2, 3 things. What 3 things is it gonna do here? One thing is very basic reaction. Another thing is gonna be the newer reaction, one of the carboxylic acid derivative reaction, and then the third thing is gonna be a newer reaction. Right? It's this last step here with the acid, water, and heat. It's gonna do 3 things to this molecule.
It's gonna hydrolyze and then decarboxylate.
Mm-hmm. Yes.
Is that it?
And what will happen to this enolate ion here?
Does it turn into OH?
It does become an OH, right? And that becomes an enol. And when we have an enol, what would that enol spontaneously do? Convert into? There is a spontaneous process that we're gonna do with that enol.
Acid base.
Acid base is gonna protonate the O minus to OH, and when we get the enol here, there's a more favored form. Tautomerization.
So does it break open? Wait, never mind.
It doesn't break open. It's gonna become a carbonyl, like that. That ring right there is like when it becomes an enol, it's gonna become a carbonyl, right? Or you could directly go to the carbonyl from this enolate ion here by making a carbonyl again and have this alpha carbon grab a proton from the acid to become a carbonyl, like that. Right. So the intermediate here is gonna look like this. Right? Where this enol here will convert into a carbonyl through tautomerization, and because we have this beta carbonyl acid, we're going to do decarboxylation because we are also given heat, right? And I'm going to go over that decarboxylation reaction after. And the final answer here is gonna be this. 1, 2, 3, 4. 1, 2, 3, 4. This is gonna be that. This is gonna be this. CH2, carbonyl, CH2, CH2, like that. This is our final answer right here. Okay, this enol here, tautomerized to this carbonyl. One of the carboxylic acid disappeared in the form of carbon dioxide through decarboxylation. Any questions on this synthesis before I go over the decarboxylation mechanism on how like one of the carboxylic acid went away into the CO2?
When should we do the 1,4 addition and when should we do 1,2 addition?
So when you have an alpha, beta, unsaturated carbonyl, which is going to be a carbonyl, and this is the carbonyl carbon, this is the alpha carbon, this is the beta carbon. There's a double bond between the alpha and beta carbon. That's the unsaturation. But there's two electrophiles here. This is an electrophile, and that is also an electrophile, right? We could clearly see why this is an electrophile. It's because it's attached to this electronegative atom oxygen, making it positively charged. It's harder to see why this is the electrophile, but it's going to be more clear if I draw you out the resonance structure. So when we draw out the resonance structure of this alpha beta unsaturated carbonyl, we can clearly see the positive charge on that beta carbon. Right. Now, because there's a full positive charge on that carbon, I think of that as a stronger electrophile, but I checked Lievens' notes. She says that this is the stronger electrophile. But this one here, if you attack that one, that would lead you to the stable product. So think of this as the thermodynamic product, like when you attack that carbon, and this one here is going to give you the kinetic product. Right? So the nucleophiles that would attack this beta carbon are going to be reversible nucleophiles. And those are things like enolate ions. So something like this, but the nucleophile is not the O-, it's that alpha carbon right there. That is the same thing as this, right? The red star is the nucleophile. It could be things like OH-, it could be OR-, it could be RNH2, it could be CN-, it could be organocuprate, if you guys learned about that yet, with the copper lithium. If not, don't worry about that. But 118b, you guys do need to know this for chapter 18, the organocuprate and the 1,4 addition. This is chapter 18 stuff for 118b, the very end of 118b. Right? The irreversible nucleophiles would attack the carbonyl carbon, and those are going to be two things. They're going to be the reducing agents, and they're going to be the organometallic reagents, right? And there's two types of reducing agents that you know, NABH4 and LiAlH4. There's two organometallic reagents you know, Grignard reagent, RMGBr, and organolithium, RLI. And you will usually see this with acid workup as well, like second step H3O+. When you see these right here, where you have an H-, which is the reducing agent, or an R-, which is the organometallic, those are irreversible nucleophiles that would attack that carbonyl carbon. Right, and the reason why we say the 1,2,1,4 addition is because conventionally, the oxygen is atom number 1, the carbonyl carbon is carbon number 2, the alpha carbon is carbon number 3, the beta carbon is number 4. So when you attack the carbonyl carbon, that's a 1,2 addition. 1,2 addition. That's also known as a direct addition. When you attack the beta carbon, you attack the 4th position, which is a 1,4 addition, also known as a conjugate addition. right? I don't like using 1, 2, 1, 4 addition because people get confused on why like this is 1, 2, 3, 4. That's just the convention of like what the people that found this reaction, they just named it like that. I like to give a direct addition or conjugate addition, but no both for vocab. Right. And if you look at this mechanism over here, we have an alpha beta unsaturated carbonyl here, and this right here is an enolate ion. And an enolate ion, we said, is a reversible nucleophile, which attacks the beta carbon, 1,4 addition, conjugate addition.
Got it. Thank you.
Yeah. Okay. So let me go over decarboxylation and when to know when to do it. So decarboxylation here is going to have a beta carbonyl acid, and the only reagent that you're going to see is heat, right? What that's going to give you is carbon dioxide, CO2, and it looks like this in the Lewis structure: a carbon with 2 carbonyls and carbonyl, whatever the carbonyl is. It could be ketone or it could be an acid, right? And it has to be beta, right? The relationship between the carboxylic acid and the carbonyl. So let's give you an example. Let's say we have this carboxylic acid here, where this is the carbonyl carbon, this is the alpha carbon, this is the beta carbon. If you put heat, the quick way to predict the product is completely get rid of the carboxylic acid, right? And that's going to give you your final answer. That's it, ketone, right? Because this carboxylic acid here is going to go off in the form of CO2, carbon dioxide. Here is the mechanism.
Question, will we have to write, like, typically, would you write CO2 on the side as well?
You don't have to. It's inorganic, so it's not required to get full credit.
Okay.
But if this was a mechanism problem, then you would have to draw out that CO2 on the side.
Right.
If this was a mechanism problem. Yeah.
Okay.
Now let's look at the mechanism here. If you're given this neutral carboxylic acid, we're in acidic conditions here. So I'm going to redraw the structure like this. I'm going to rotate this single bond between the carbonyl carbon and the alpha carbon. And that's going to give me this intermediate right here. Right, this structure here is the same exact structure as this. This is the carbonyl carbon, this is the alpha carbon, this is the beta carbon. The carbonyl carbon has the carbonyl group, and the OH is up here now. I explicitly drew out the bond between O and H now to show the mechanism clearly. This H here is partial positive charge, this oxygen here is partial negative charge. They are very attracted to each other because they can do H bonds with each other, right? And they have opposite charges. Opposite charges attract. So this oxygen here is going to grab that hydrogen, right? Using one of its double bonds. The bond between this hydrogen and oxygen there is gonna create a double bond right there between the carbonyl carbon and oxygen, right? This is where we get our CO2. That's where we get our CO2 right there. Now we're gonna break this bond between the carbonyl carbon and alpha carbon to create a double bond right there to give us this intermediate here, right? And that gives us our carbon dioxide, which is this here, right? And then we already know that this is an enol, which will tautomerize into the carbonyl form. Any questions on this mechanism? Now, the relationship between the carbonyl and carboxylic acid has to be beta to each other for this to work. If you have a carbonyl that is alpha to the carboxylic acid, that's too close. That's not beta, so no reaction. If the carbonyl is alpha, beta, gamma, delta, epsilon, something after epsilon, I forgot, that is gonna be also no reaction because that's not beta. That's too far away. It has to be exactly beta to the carbonyl, to the carboxylic acid, right? The carbonyl has to be beta to the carboxylic acid for this decarboxylation reaction to work.
And just to clarify, so it's any type of beta carbonyl like reacting like with heat.
Yes, any type of beta carbonyl reacting with heat will convert the carbonyl into this carbonyl here and just get rid of the carboxylic acid like that.
Okay.
Yeah.
Okay.
Because the ones that I've been giving you are ketones, right? But it could have been another carboxylic acid like this. And when you react this with heat, only get rid of one carboxylic acid. You could get rid of this carboxylic acid to give your final answer, right?
Okay.
Or you could get rid of this carboxylic acid to get your final answer.
Okay.
So this is our final answer here, plus CO2 if you want to draw that out. Okay. And if let's say this had an R group there and this had an R group like that, that would be this right there, right? Because this is the blue carbon right there that has a methyl group and an ethyl group, methyl group and ethyl group like that. The CO2 here, one of it is just gone. It got emitted off as CO2 gas, carbon dioxide gas.
Okay, perfect. Thank you.
Yeah, this is very important here because this is going to let you know the differences between malonic ester synthesis and acetoacetic acetoacetate synthesis, right? When you have a ketone beta to a carboxylic acid, that's acetoacetate synthesis. When you have a carboxylic acid beta to another carboxylic acid and you just get rid of one of them, that's malonic ester synthesis. That's what we just did previously right here, right? We see that we have two esters here that will eventually become the carboxylic acid through hydrolysis with the acid water, right? But then because of the heat here and this carbonyl is beta to this carboxylic acid, we do decarboxylation as well. We completely get rid of one carboxylic acid and keep one of the carboxylic acids in there, right? And then these new R groups here, they weren't there before in the original molecule. We added these two new R groups through these reactions here, right? Through enolate alkylation. We alkylated the enolate ion, the alpha carbon, alpha alkylation, right? There's three enolate alkylation reactions that you need to know. The SN2 reaction with the primary alcohol, the 1,4 addition or conjugate addition with the alpha beta unsaturated carbonyl, and the other one that I didn't show you guys yet, which is epoxide ring opening, right? And because this is basic conditions, we're gonna open up the epoxide in the less subside. So I'm gonna go over that when I go over the next reaction, which is gonna be acetoacetate synthesis. Right. Before that though, any questions before we move on? Okay, let's move on to acetoacetate synthesis. And I'll give you guys some practice problems to work on. And then I'll move on to 118B. So we got acetoacetate synthesis. And since 8B has a quiz tomorrow and the final on Monday, and 118B has their final next Friday, I'll try to spend more time with 8B tonight because you guys have like your finals coming up sooner and you have your guys' quiz tomorrow. So let's go over acetoacetate synthesis here. That's gonna be, let's say, your starting material is gonna be ethyl acetoacetate, which looks like this. Let's say we react it with these reagents here. Okay, so the first reagent, strong base, ethoxide ion. That's gonna look for the most acidic hydrogen. That is gonna be this alpha hydrogen right here. So when I draw out the mechanism, grab that hydrogen, give a negative charge on that alpha carbon to get this enolate ion, where the nucleophile is the alpha carbon. That's the star carbon. Now bring in the second reagent, this primary haloalkane. This is our dot carbon. star carbon attack the dot carbon, kick out the leaving group bromine, SN2 reaction. Now connect the star and dot. This is the star, this is the dot, that's the new bond between the star and dot. The dot is attached to 1, 2, 3 carbons, 1, 2, 3 carbons. The bromine is no longer there, we kick that out. Bring in the third step, which will deprotonate the other alpha hydrogen to create another enolate ion, another starred carbon, another nucleophile. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. Negative charge there. Starred molecule here. Now, let's do the epoxide, right, reagent. We are still in basic conditions. We did not add this acid in yet, right? Even though you see acid in the reagents arrow, do not think that you're in acidic conditions just yet, right? That's gonna come later. We are still in basic conditions because we still have ethoxide floating around, and there's no acid yet. There's no H2O plus, no H2SO4, no HCl yet, right? So when you have this negative charge nucleophile here with an epoxide, we're gonna open up the epoxide at the less sub carbon, which is this red dot right here, not this carbon. That's more sub, right? We're gonna attack the less sub carbon. So star attack dot, this bond here breaks and goes onto the oxygen right there. Now, you guys should practice connecting these two together because connecting epoxides when you open them could be tricky, right? But it should look like this right here. 1, 2, 3, 4, 1, 2, 3, 4. This is the starred molecule carbon. This is the dot carbon. New bond between star and dot. And if this is epoxide, I like to also keep track of this carbon here, which I just color coded in green, right? Because that green carbon is still attached to the oxygen, right? This red dot is attached to the green dot always, right? But there's no more bond between the red dot and oxygen. We broke that bond when we attacked the epoxide and opened it up. But this oxygen here is still bonded to the green dot, which is that single bond to O minus like that. And this green dot here is attached to the isopropyl group like that. Okay. Any questions on that mechanism, on how I open up the epoxide and how I got to this intermediate here?
We are in basic condition because like we have hydroxide before, right?
Yes, we are in basic conditions because we have O or minus ethoxide. Yes, we have bases around. Correct. Yep. So this is like review back to 8A, I think, when you guys learned these reactions, opening up epoxides and the less subcarbon and SN2 reaction, right? But this is the new one for 8B, the 1,4 edition or conjugate edition. Yeah, this stuff right here. This is the new stuff for 8B. Okay, now we bring in the fifth step, which is gonna do 3 things. What 3 things is it gonna do to this intermediate? When we bring acid, water, and heat.
Tautomerize.
Tautomerize. We tautomerize enols and enolates, right?
Yeah.
When we protonate this O minus here, it becomes OH. Is there alkene here or here?
Oh, no, there isn't.
No, yeah, so we don't do tautomerization here. It just becomes a neutral OH.
Okay.
Right? If there was an alkene there or here, we do tautomerization and convert that into a carbonyl. Right?
Yeah.
And that's the case when we do the 1,4 addition or conjugate addition with that alpha beta unsaturated carbonyl. Right? Okay. So acid-base reaction, protonate the O minus to OH. That's the first thing. There's 2 more things that's gonna happen to this molecule.
Hydrolysis.
Hydrolysis of the ester into the carboxylic acid.
Carboxylic acid.
Right. And after that, we're gonna get this intermediate right here. But because we have heat, something else is gonna happen as well.
Decarboxylation.
Yes, decarboxylation. Yeah, this is our intermediate right here. After we protonated the O- to OH, we hydrolyzed the ester carboxylic acid derivative back to the default functional group carboxylic acid, doing hydrolysis or alcoholysis. But because we have heat and we have a carboxylic acid, where beta to the carboxylic acid, there's a carbonyl, we're going to do decarboxylation, where we completely get rid of the carboxylic acid, and that gives us our final answer, right? So I'm going to draw it like this. 1, 2, 3, 4. 1, 2, 3, 4. Boom. Boom. And coming up with this alpha carbon, 1, 2, 3, 4. 1, 2, 3. 4. One more carbon. Like that. Okay. This is our final answer here. That is acetoacetate synthesis. Exact same synthesis route as malonic ester synthesis. Exact same thing. Exact same process. The difference between acetoacetate synthesis and malonic ester synthesis is the carbonyl that is beta to the carboxylic acid, right? When we do decarboxylation here for acetoacetate synthesis, the carbonyl that's beta to the carboxylic acid is a ketone. That's how we get the ketone in the product. For malonic ester synthesis, when we do decarboxylation, the carbonyl that's beta to the carboxylic acid is another carboxylic acid. So that's why we get that carboxylic acid in the product. That's the differences in the products. The differences in the reactant, the starting material, is that malonic ester synthesis has 2 esters to begin with. Whereas the acetoacetate ester synthesis has 1 ester to begin with and 1 ketone, and that ketone stays the same all throughout. Here's a conceptual question for you guys. Why couldn't I start off our molecule like this? And let's say I want to get the same exact product from the exact same reagents. Right, let's say I try to do that. Because this molecule here does have 2 alpha hydrogens for us to deprotonate and add 2 new R groups, right? And these are carboxylic acids that are beta to each other, so we could do decarboxylation, right? So let's say because this is a ketone right here, we keep that as a ketone as well. Why did we have to start why can't we do this right here? Why can't we start with a carboxylic acid? What would happen instead in the first step?
It would be an acid-base reaction.
Yes. It would be an acid-base reaction because we have this acidic proton right here. Acidic. So this strong base here is going to grab the hydrogen, and the bond between the hydrogen and oxygen there is going to go to the oxygen to give us this answer instead. The carboxylate, right? We're not going to form this. We're going to form this. And then when you try to bring in the second step, no reaction. There's no strong nucleophile here. Why is this O- not a strong nucleophile? Like, why can this O- here attack this carbon and kick out the bromine right there? What can it do with this carbonyl here?
Resonance.
Resonance, which makes it more stable. And because it's more stable, it's less reactive, aka weak nucleophile. So this O- here is a weak nucleophile. No reaction when we put in an electrophile to there. So this is going to be our final answer there.
I have one question going back to like the end product of the acetyl acetate that we just did. Whenever looking at it, like at that end product from the like that in between step, the second to last step, where did that bond come from? Like you got rid of the carbonyl and the OH, right?
Yes, this one
Got
here.
rid of that, and then
Uh-huh.
the new bond. Like I'm just trying to wrap my mind
Uh-huh.
around how you drew it.
Oh, to
Make
this
sense?
how I drew this one or how I
Yeah.
drew this one here?
It's like the same thing, right? You're just getting rid of the.
Oh, yes, it's the same thing, right? But I flipped this whole structure here up, right? Because there's free space up there now,
Okay.
right? Because if I just like get rid of it, I could have drawn it like this as well, but look, that looks a little bit awkward. It looks
Right.
weird. So I just flinged it up there because there's free
Okay,
space
so it's
there
like
now.
flipped upside down. Okay, got it.
Yeah, yeah.
Okay, thank you.
Yeah.
I have a bit of an unrelated question.
Mm-hmm.
There was a question on the homework that was similar to this,
Mm-hmm.
but it formed a ring with the reactants. So it was like,
That might be intramolecular Kleisel condensation, but send me a picture of it and I'll see. Right.
oh, okay.
Uh-huh. And also, like the second step would not do anything with the carboxylate. The third step would probably deprotonate the alpha hydrogen to create negative charge there, and then you could probably do that. But this is the answer after the first step here. You get that carboxylate. Okay. And then once you have that carboxylate there, you can attack this epoxide, open it up, and then you could like protonate these and do decarboxylation after, probably. But that's why in acetoacetate synthesis and malonic ester synthesis, our starting material is an ester, because that ester does not have an acidic H, right? So we don't have to worry about deprotonating that acidic H. We're gonna deprotonate the alpha H, which is the most acidic H here, if there's no carboxylic acid, right? If there's a carboxylic acid, that carboxylic acid H is more acidic than this alpha H, right? So that's why our starting material has esters, to make this alpha H the most acidic one for these synthesis reactions. Oh, okay. Yes, I see. So let's go through this practice problem. This is actually a good practice problem here. Okay. So I don't think you guys need to know the name of this, but if this is our starting material here, are we doing malonic ester synthesis or acetoacetate synthesis? If this is our starting material.
Malonic.
Yes, malonic. Just in case it shows up on vocab. Okay, so first up, we got NaOET. When you see Na, positive charge. Whatever is attached to it, negative charge. So our negative charge here is OET, ethoxide ion. This is a strong base. That's going to deprotonate the most acidic hydrogen, which is the alpha hydrogen, right? We don't have a carboxylic acid, so we don't have to worry about that. We're going to put a negative charge on the alpha carbon to create our enolate ion, our nucleophile. Right there. Now, we're going to bring in the second reagent, which is going to be this dihaloalkane. And we're going to use one of the carbons here to make it our dot and kick out the leaving group. It could have been this one as well, right? But because this is symmetrical molecule, it doesn't matter. You're going to get the same thing if you attack either one. And that's going to give us this right here. This star molecule is going to be attached to that dot carbon. That's the new bond. The dot carbon is attached to 1, 2, 3 bromine. 1, 2, 3 bromine. Okay, now let's bring in another NaOET, ethoxide ion. This is a strong base. It's going to look for the most acidic hydrogen, which we do have another alpha hydrogen to deprotonate and make another enolate ion. make another starred carbon on the alpha carbon. Right? But from here, they didn't give us another electrophile before the hydrolysis and decarboxylation steps, right? But we do have an electrophile here somewhere. Right? We do have a dot somewhere here. This is our start here. We can attack something and kick out a leaving group, which is this carbon right here. This is our dot. So we're going to do an intramolecular reaction here because the nucleophile, the starred carbon, is on the same molecule as the electrophile, the dot carbon. So we're going to attack that dot, kick out the leaving group, and that's going to form a 1, 2, 3, 4, 5-membered ring. So when I draw out the intermediate, it's going to look like this. This is the starred carbon. I know I'm making a 5-membered ring, so that's my template right there. This is my dot carbon. This is the new bond between the star and dot carbon, where the way that I numbered it, this is atom 1, this is atom 2, this is atom 3, this is atom 4, this is atom 5. 5-membered ring. New bond between 1 and 5 right there when we close the ring. Any questions on that? That was the intramolecular reaction right there that made that ring.
It's just like the mechanism makes sense, but like when I was doing it, that's not what I thought of. I went straight to like making it linear. I didn't think to like for this to be intramolecular, so I know this is probably just like remembering things, but how do we recognize that?
You could recognize that you're going to make a ring if your nucleophile is on the same molecule as the electrophile. If the starred carbon is on the same molecule as the dot carbon. They're the same molecule. So the molecule is attacking itself.
Okay.
Closing the ring. Right. Like if you look at this entire molecule here, it has the star molecule and the dot molecule on the same molecule. Right?
Yeah.
In the previous examples we did, the star and dot molecules were separate. Right? This is a starred molecule here. This is the dot molecule here. They're separate. They're not in the same molecule. That's intermolecular.
Yeah.
Right? But in this reaction here, they're in the same molecule. So that's intramolecular, forming the ring.
Okay.
Yeah.
The thing is, so it has NeOET as the first step, then the haloalkane as the, or the haloalkane. Yeah, as the second step. But when we're doing the mechanism, we go with the second NaOET, and then that's like the second step, kind of. Oh no, never mind. That is the D. Sorry.
The third step base is the second equivalent of base that will deprocynate the second alpha hydrogen to create that alpha carbon negative charge again.
Yeah.
Right. But then after that, they don't give us another electrophile that we're used to seeing, like epoxide, alpha beta unsaturated carbonyl, or another haloalkane. But we do have a haloalkane within the same molecule as the starred carbon.
Yeah. Okay.
Yeah.
That makes sense.
Yeah. Now the last step is gonna do two things now. Hydrolysis first to hydrolyze the esters into the parent functional group, carboxylic acid. And then because we also have heat, right? And we have a beta carbonyl acid, we're gonna get rid of one of the carboxylic acids to get our final answer. That carboxylic acid with the ring right there. Okay. Nice. Any questions before I give you guys practice to try on and move on to 1 B?
Actually, I had another question, but it wasn't about any of this. It was just a question that I was working on, and I was stuck on.
Yeah.
So I was doing some of the practice, and one of them is I think it's a butanoic acid reacting with LiLH4. I didn't. Is the final? Yeah, that is the product. Just a primary alcohol.
That's it.
But then in the key, there was a methyl group on carbon 3.
I
Like
saw
this?
that one too. That
Yeah.
Okay, I know what you're talking about from the practice problem like sheet.
Yes.
Okay, yeah.
Is that a mistake?
There is another problem that's like that as well, I think, on that sheet.
Like it's the same kind of answer?
Yes.
That's so weird.
Let me see if I can find it real quick. I was trying to do that earlier too.
I don't know where that methyl group came from. I don't know. Are
Yeah,
these the only reagents?
Yeah, that's it.
That's not supposed to be there.
Yeah.
Yeah, that's not good. No.
Wait, okay, so how it works is an H minus goes and grabs the acidic hydrogen.
What? This reaction here, this mechanism,
Yeah.
it reduces the carboxylic acid into the primary alcohol, so you just completely get rid of the carbonyl.
Yeah, but is it by grabbing the acidic hydrogen on
That's the first step. Yes, it's gonna grab the acidic hydrogen first, and then once you get the carboxylate, that's gonna do something. But don't worry with the mechanism. You don't have to worry about the mechanism for reduction here.
Okay, that's good because I was trying to find it in my notes. And I couldn't find it.
Yeah. Don't worry about it. Don't worry about it. She did not go over it. Right.
Good.
Just in case you're curious on how we can get to here, right? What is this carbon here? The second carbon relative to the carbonyl carbon?
It's the alpha.
Alpha carbon, yes. How can we alpha alkylate it? Like, what do you think we could do? How can we make that alpha carbon negatively charged?
ALH3. Because the Li is a positive charge. So we already
is a reducing agent. So that's gonna do reduction. Think about like the reactions we've been doing. Like, how have we been alpha alkylating? What reagent did we use?
Oh, we're using a base?
Base, yes, a base.
Okay.
But if we put in that base right there, it's not gonna get this hydrogen. What's the problem? Like, what?
Oh, it's gonna do acid base.
With what? It will,
with
but
the OH.
Yes, with the OH. But we want to do acid base with the alpha H, right?
Yeah.
What can we do to convert this carboxylic acid into an ester?
Carboxylic acid. Wait.
This is one of the carboxylic acid derivative.
Fischer esterification.
Fischer esterification. So we're gonna use this alcohol here with H2SO4 because this can only happen in acidic conditions. It can never happen in basic conditions, right? Because basic conditions would deprotonate the carboxylic acid like that. Right. Now, once we have that, then we can bring in the base with the solvent to create the enolate ion on the alpha carbon. And now, what can we do to add that methyl group there? Like, let's say this is my starred carbon, which is the starred carbon here, and this is my dot carbon here. What can we do to add that methyl group right there?
Would it be an No, it wouldn't be an organic.
This is the new bond between the star and dot. Let's say this is my dot right here. Or actually, yeah. This is my dot right here.
Would it be an
Think about a leaving group. So this right here is a CH3, right? So it would be CH3Br.
BR? Okay.
Or
wait.
Cl or I. Any good leaving group.
So RX.
Yes, RX. And whatever the R group here, in this case it's the methyl group, that's that R group right there. Right. Star attacks the dot, kick out the bromine.
Oh, kind of like what we did in the previous one, where we
Right.
Oh, okay.
If it was like this, then your R would be like this. and that would be your dot right there, like that,
Yeah.
right? But because this is just a CH3, that's our CH3 right there, right?
Okay.
Now, what can we do to convert the ester into the primary alcohol? It's one of those reactions as well, in the chart.
Ester to primary alcohol. That would be the reducing agent.
Yes, reducing
LAO.
agent and acid workup. That's how we could get there if this was a synthesis problem.
Yeah, okay, I was gonna say this is synthesis.
Yeah, this is synthesis. 8-beat probably doesn't do synthesis, right?
I hope not.
Yeah, I don't think so. Hopefully not. Because you guys haven't been
Yeah.
practicing synthesis, so it wouldn't be fair if it shows up.
Right? Yeah.
Yeah, I know. But all these reactions you do need to know though, like for predict the product.
Yeah.
Or maybe like mechanism. Especially like this is mechanism. Good. This is mechanism. This is also mechanism. Do not need to know the mechanism for this.
Okay, that's good. I feel like synthesis is good practice if I had time to. Is it like I feel like it would be easier to predict products and stuff with it.
Yes, I know. It's like once you know the reactions, then like that's when you practice with synthesis. It's like a puzzle, kind of. Like reactions are like the tools in your toolbox, you know, to solve these synthesis problems. I know.
Yeah.
Did you guys ever do synthesis in 8 series?
She sometimes shows examples and she kind of goes through them really fast, but like
okay.
never like in-depth synthesis. She doesn't explicitly say it.
I see. Dang.
Yeah.
Well, yeah. Oh my gosh. Okay, let me give you guys one problem to try out. And then I'll do 118B and then 118A after. Yes. Okay, try these ones here. This one is going to require more steps than what we've been doing. But take a screenshot of this and try it out. Okay. (118B). I saw your email, Kelly, on 118A Cagley last lecture. So let me know what you want to go over for that. And we can go over it. When is the final again, Kelly, for 118A for Cagley? And Layla, what did you want to go over for 118B? I created a document of like chapter 17, chapter 18 summary table of all the reactions you need to know. So I'll be sending that to you on Instagram after the session, right? So then you can review those and then let me know what topics you want to go over for our session tomorrow, and then I'll prepare notes and practice problems on those topics that you want to go over. Tuesday, okay, that's good. But right now, since like office hours is running out of time, we could go over one topic and one problem, and then I'll send you those notes and let me know what topics you want to go off of that. Layla, for 118B. Okay. Okay, the Davidic reaction. Yes. So the Davidic reaction, gotta make sure with the illid and carbonyl here really quick, because I gotta double check before I show this reaction, because it's easy to get this mixed up. Davidic reaction. Let's see. This one. Yes, right here. Okay. So, Vedic reaction. It's gonna be two reactants. You can have a carbonyl plus something called an illid. And that's gonna give you an alkene. Right? But we can categorize the illid into two things. We could categorize it in the unstabilized illid, and the stabilized illid. An unstabilized illid is gonna be like unable to do resonance, whereas a stabilized illid is able to do resonance. Right. So I'm gonna give you guys examples of each. So we already know what a carbonyl is like, right? It could be a ketone, it could be an aldehyde, like that. In this case, we're gonna focus on ketones and aldehydes. There's more carbonyls like carboxylic acids, esters, amides, acyl and hydrides, but that's for 118C. We're gonna worry about ketones and aldehydes here. An illid is gonna be something like this. When you have a carbon double bonded to a phosphorus pH3, right? This is the illid portion right there, right? And that is the exact same thing as this. Because these are just resonant structures of each other, right? This yellow highlighted portion right there is the illid part. And this is unstabilized because this double bond here, or this pair of electrons here, cannot do resonance with anything at all, right? It can't do resonance because this is an sp3 roadblock. But if it is able to do resonance, like this, or like that, this yellow highlighted portion here is the illid. This is a stabilized illid because this illid here can do resonance with the rest of the molecule, like that. Right? The unstabilized illid would lead to a Z alkene. The stabilized illid will lead to an E alkene. Right? Z or E depending on what the illid is. Now let's be more clear and give you a specific problem. So if I have this aldehyde right here, and I react it with this illid right here, this is how I would predict the product right here. Wait, actually, let's not put a ring yet, because that's not gonna. Yeah, let's start simple first, and then I'll put that ring after. So this right here is my carbonyl. This right here is my ylid. To make the double bond, right? This is gonna be my red carbon. This is gonna be my blue carbon. We're gonna make a double bond between the red and blue carbon. Right. This is just predict the product quickly without doing the whole mechanism. So let's draw out that red carbon like that. And let's draw out the blue carbon like that. Because this is an unstabilized ylid, right? This is gonna be an Z alkene. So this could be a double bond between the red and blue carbon. The carbonyl goes away, the PPH3 goes away. And because I want to make the Z alkene, this ethyl group here has to go down in the same side as this propyl group to make that a Z alkene. Now let's use the same carbonyl, but this time, let's say our ylid here is resonance stabilized. It could do resonance with the carbonyl here. Right? Let's do the same thing. Let's draw that red dot out, make a double bond between the red dot and blue dot. The carbonyl goes away, the PPH3 goes away. And because this is a stabilized ylid, I'm going to make a Z alkene. So this structure here is going to be going on top, on the opposite direction as that group right there. So that's how we would predict the product quickly for Wittig reactions. Right, that's how we could do it quickly for Wittig reactions. Now, let's go over the mechanism of what that would look like. So for the mechanism, let's look at the top one here. This is my aldehyde. This is my ylid. I'm going to draw out the resonance structure of the ylid by pushing that double bond down there on that carbon to give me a negative charge on this carbon right here and a positive charge on the phosphorus right there. This negative charge carbon here is my star carbon. This carbonyl carbon here is my dot carbon. The star carbon is going to attack the dot carbon, push the bond onto oxygen, and give me this intermediate right here. Right, where this is the star carbon, this is the dot carbon, this is the neo bond between the star and dot carbon. The dot carbon here is attached to an ethyl group, like that. Okay, now the next step here is that this O- here is going to attack the positive phosphorus to create this box, this ring. Okay, now from here, right, think of this group here as like very like they want to leave the molecule right away. So we're going to make a double bond between the oxygen and phosphorus like that. And that's going to break a this bond here, creating a double bond right there. And that leads us to our final answer. So the mechanism is pretty weird here for this Wittig reaction. But that's our final major organic product, which is going to give you full credit for predicted product. But this is also the leaving group that just left, but this is inorganic. There's no carbons or hydrogens there. So that's where the carbonyl went, and that's where the phosphorus PH3 went. Right, but this right here is a Z alkene because we have a unstabilized ylid right there. Now to create the ylid, right, you might see something like this. You might see a haloalkane like that, and you might see first step PH3P, where the P has a pair of electrons, and then second step you might see aldehyde like that, right? And this is going to be a big sign of Wittig reaction because the first step here is going to create the ylid, right? The first step is going to have the phosphorus attack the carbon, kick out the leaving group bromine to give you this PPH3 positive charge, but this is not exactly our ylid yet because we need a negative charge on this carbon here attached to the phosphorus. And to make that negatively charged, we have to deprotonate it. We have to deprotonate it by using a strong base like N-butyllithium. This is 1, 2, 3, 4. This is N-butyllithium here. Right? That N-butyllithium is going to grab this hydrogen and put a negative charge on that carbon right there. And that's going to give us this ylid here, where there's a negative charge on that carbon, a positive charge on this phosphorus, and then we do the carbonyl to do the ylid reaction. Where to predict the product quickly, this is gonna be my pink dot, this is gonna be my purple dot, and because that's an unstabilized ylid, I'm gonna make a Z alkene. This is the pink dot, this is the purple dot, make a double bond between the pink dot and purple dot. The purple dot has an ethyl group, and I'm gonna make that go down because I want to make a Z alkene. Right. So this right here is most likely to show up on predicted product problem, where you have a haloalkane right here, and you convert that haloalkane to an ylid by 2 steps. The first step is to put pH3P to add that pH3 there with positive charge, but this is not exactly our ylid yet because we need a negative charge here on that carbon directly attached to the phosphorus. To do that, we deprotonate it with a very strong base, N-butyllithium. Once we have the ylid, right, we bring in any carbonyl we want to create the alkene. Now, I'm going to give you a practice problem for you to try, and then I'll check it later for probably our session, or send me the DM of your answer. But here is going to be the problem here. Let's say I have this right here, and I give you these reagents. First step, pH3P. Second step, N-butyllithium. 1, 2, 3, 4. Third step, we get this carbonyl there, right? pH3 and lithium. Okay, yes. Try this one out, Layla, and send me your answer once you get it, and I'll let you know through text if you got it correctly. Okay. Yeah. Of course. Okay. So let's go back to 8B and check you guys' work right here. I see Maggie sent hers on the Zoom chat. For you guys can send it on the Zoom chat as well, or text me through the phone, and I could check your guys' work as well. So let me open it up. Okay, the first step, you deprotonate the alpha carbon, get the enolate ion. Second step, you added that group, 1, 2, boom, good, 1, 2, good. Third step, deprotonate, good, and then, oh, you got stuck there. I see, stuck there. Okay. Yes, that is the part where Jenna also got stuck when we went over this problem earlier. Okay, let's see Chris's work. Deprotonate, create the alpha carbon, negative charge, attack that SN2 reaction. 1, 2, 3, 1, 2, 3, ring there, 4, 5, correct. Deprotonate the second alpha hydrogen, create a negative charge there. And this step here is the confusing step, right? This is an intramolecular reaction. That alpha carbon that's negatively charged, the starred carbon, is gonna attack that dot carbon, kicking out the leaving group. And because the starred carbon is on the same molecule as the dot carbon, this is an intramolecular reaction creating a ring. But be careful here, Chris. Let's see how many membered ring we're gonna form, right? We're gonna form a 1, 2, 3, 4, 5, 6 membered ring. If you count your number 1 carbon as the negative charge carbon, and you go all the way to the carbon being attacked, you're gonna make a 6 membered ring. 1, 2, 3, 4, 5, 6. So when you draw out the intermediate, make sure that's a 6 membered ring. But then the rest of the steps is good. Looks good. You hydrolyze the ester, and then you decarboxylation. And then that's where you got stuck, right? At the 5th step. So I'll go over that when I go over the answers. Okay. Did that make sense, Chris? Did that make sense on why it's a 6-membered ring instead of a 5-membered ring for the intramolecular one?
Actually no, but like I will hear your explanation after you.
Okay. I'll explain, and I'll tell you what you did. Okay, so first step, deprotonate the alpha carbon, create a negative charge there. So you guys got that so far? That's my starred carbon. this start carbon here is going to attack this dot carbon, kick out the leaving group to give us this intermediate right here. This is the start carbon. This is the new bond between the start carbon and dot carbon. This dot carbon is attached to 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. BR. 1, 2. Ring right there. Wait, let me see Chris's work again. See. 1 dot 1 2 dot 1. Yeah, that's right. Okay. So now that's the end of the second step. The third step is gonna bring in another base to grab that hydrogen and put a negative charge on that alpha carbon. Right, this is the start carbon. This is the dot carbon. Right, this is where you got stuck, Maggie. The next step is an intramolecular SN2 reaction, like the question that Jenna sent earlier. Right, we don't see another electrophile after the third step. The electrophile is here on the same molecule as the start carbon. This start carbon is the same molecule on the same molecule as the dot carbon. So it's gonna attack that dot carbon and kick out the leaving group. And this is where you made the mistake, Chris. We're gonna make a 1, 2, 3, 4, 5, 6 membered ring. So when we draw out the intermediate, it's gonna look like this. Yeah. You drew out a 5-membered ring, which was the example that Jenna sent earlier. Right? That was a 5-membered ring. But in this example, we're gonna make a 6-membered ring, which looks like this. Where this is the start molecule, this is the dot molecule. This is gonna be 1, 2. Actually, let me make the dot molecule dot carbon.
Yeah, I forgot to count the original one.
Yeah, right. Did you just think about the example that we did earlier in office hours with the 5-membered ring? And that's why you drew out the 5-membered ring?
Yeah.
Yeah. I know. So even you guys do practice, right? Like don't like fully rely on the practice and don't memorize it. Try to understand it and like do everything step by step procedurally, so then you don't fall into those traps and avoid making those mistakes. Now we see at carbon 4, that's that phenyl group there. So I'm gonna add that phenyl group right there. The benzene right there. And then everything else is good. Now, the next step, the fourth step, is gonna hydrolyze the esters into the carboxylic acids as the intermediates. Right? But we don't stop there because we also have heat. And we see that these two carboxylic acids here are beta to each other. So we're gonna do decarboxylation. We're gonna get rid of one of the carboxylic acids to get this here. Right. Across from it is a phenyl group. Just like this. Okay. Now, once we have that, we don't stop because this fifth step here, when we have alcohol with acid workup, what is that going to do? This is our alcohol here. Not acid workup. This alcohol here with H2SO4 acid. What is that going to do with this carboxylic acid here? It's going to be one of the carboxylic acid reactions in the chart. That is going to convert the carboxylic acid into an ester. Fischer esterification, like that. Okay. And that is the final product there. So this right here was malonic ester synthesis, right? Steps 1 of 4. And then the fifth step was Fischer esterification. Yeah. the Malonic acetoacetic product is this one, and then we use that to convert this carboxylic acid into this ester using the alcohol and H2SO4 reagents. Okay.
Wait, can you go back to the first page?
Yeah.
I made a 5-membered ring.
A 5-membered ring. Did you get this
Yeah.
as your intermediate after you added that R group in? Like, did you get this extract structure right here?
Yeah, wait, let me count. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. And then I added the ring.
And then you added the ring. Like, is this your number 1, 2, 3, 4, 5,
no.
6?
I counted from the dot, or
oh
Yeah,
yeah.
I think you are
so-
making the same mistake as me. You can't forget to count the number 1.
Yeah, you forgot to count the start carbon.
Yeah.
Did you guys
okay.
start from here?
Yeah.
2, 3, 4,
Yeah,
5?
I did the same.
Oh, shoot.
You start from the start
Oh.
carbon. You start from the nucleophile. That's your 1
Okay.
right there. Yeah, not this. This is your 2. Yeah, that's good. We're making the mistakes now. Yes.
Hopefully not on the quiz.
Yes, I know.
Okay.
Mhm.
And then 6-membered ring.
And at carbon 4, there's the benzene ring there, phenyl group there.
Wait,
at
and then
carbon 4.
what happens after this step? This is where I got stuck.
Did you get to here?
Yeah.
Now, this is when we bring in the HCl, water, and heat. The acid hydrolyzes the esters into carboxylic acids.
Okay.
And then the heat decarboxylates it, gets rid of one of the carboxylic acids to get this structure here. Right.
Wait.
Which is this structure here. This is gone.
Okay, yeah, to get rid of the carboxylic acid, and then we would have CO2 on the side.
Yeah.
Okay.
Yeah.
Okay, I see it now. And then the ROH H2SO4 is gonna hydrolyze and no, not hydrolyze, sorry. It's gonna be Fischer.
Yes, Fischer esterification. Yes, convert that carboxylic acid to the ester. If you want to convert the ester back to the carboxylic acid, that's hydrolysis.
Okay.
Yeah, but
Makes
this
sense.
is Fischer esterification.
Okay.
Yes. Okay, that's good. Good luck on the quiz. Yes, of course. How are you guys feeling now about it? That was the new material after Claisen condensation. With the malonic ester acetoacetate ester synthesis decarboxylation, those are the new reactions after Claisen.
Yeah, I was focusing so much on like carboxylic acid derivatives, like everything except carbohydrates, and now I forgot everything about carbohydrates.
You forgot everything about carbohydrates? Oh my gosh.
Yeah.
There's 3 reactions that you need to know about carbohydrates. There's like the excess NaOH, excess CH3I one. There's the hemiacetal formation one and acetal formation one, where it changes the stereochemistry at the anomeric carbon and only the anomeric carbon. Like, remember those reactions? Yeah.
Is that the cyclicizing sugars?
Cyclizing sugars, that's last quiz. When you make the alpha and beta anomer. That's something else.
Wait, she said it's on the quiz.
Oh, it is cyclizing sugars? Like from a linear projection? Oh, okay. Oh my gosh.
Yeah, we need to talk a lot about cyclic sugar last quiz.
Oh, like you guys didn't close the ring? You guys didn't cyclize sugars?
We make it a ring, but it's just that.
Oh, okay.
Yeah, it says H reactions of cyclic carbohydrates. Disaccharides.
Yeah, reactions of cyclic carbohydrates. So it was those 3 reactions that I talked about earlier.
Okay.
Yeah, like not cyclizing carbohydrates, but reactions of cyclized carbohydrates. So she's already gonna give you a cyclized carbohydrate, and she's gonna give you reagents to react with those closed rings. You're not closing a ring. She's gonna give you a closed ring, and you're gonna react with those closed rings.
And it's gonna stay a closed ring.
Yeah. Yes, it's gonna stay a closed ring. Yes.
Okay.
Mm-hmm.
Okay,
Yes.
that's fine, I guess.
Yeah. I know. And after that, there's the carboxylic acid derivatives with that big chart, the big chart that we
Yes,
made.
that was so helpful.
Uh-huh. I think Lievens also posted a chart too on the canvas, like her own version of
Yeah.
it. Yeah. So
Yeah,
that's
she did. I saw it.
also good. Yeah. And then
Yeah.
the ones that we just did, Clayson the Clayson was last night, but then the acetoacetate, malonic ester, and decarboxylation. It's a lot. It's a lot. In 20 minutes, 20-minute quiz.
Yeah.
Oh my gosh.
I'm so curious what the mechanism question is gonna be. There's so many
Mechanism,
options here.
I think it's gonna be one of the nucleophilic acyl substitution in acidic conditions, like Fischer esterification or hydrolysis of something, hydrolysis
Low-key,
of
yeah.
ester or amide, or intramolecular nucleophilic acyl substitution, making a ring. Like I think it's gonna be that.
No, yeah, I believe you.
Yeah.
I think that's okay.
Mhm.
Anyways,
Yeah.
thank
good.
you so much.
Yeah, of course. Good luck tomorrow, guys. Good luck on the quiz.
Thank you.
Thank you.
Good night.
Good night.
Good night.
Good night.